Easier for you. Okay, so interpreting sketching graphs. One thing to look at here is what's happening with our slope. So last year for our slope, we didn't use the word slope. We used the word rate of change. And that's what we're going to focus on for today's lesson, is the rate of change and what does it mean. For your rate of change, you really want to look at your units. Right? For example, meters per second, that will be telling you speed. Okay, so you want to look at your units because they're going to be descriptive for you as well. So first of all, when we have a straight line, that means that we have a constant rate of change. Oops. It doesn't mean that there isn't a rate of change, that no change is happening. But if we have a straight line, it's a constant rate of change. And then if we have a curved line, that means the rate of change can be increasing. And that line will then be going up. Whereas if it's decreasing, if the rate of change is decreasing, the slope is going to be decreasing, and the slope will then be curving down. Okay, so whether the slope is curving up or curving down will tell you whether the rate of change is increasing or decreasing. As well, when you're making your graph, you have to come up with your x and your y values. So here is going to be your dependent values. It's what you measure. Dependent. So this is what you measure. This is your range. It's your y values. On the other axis, we have our independent. Okay. And this is called the domain, and it's your x values. Okay. Time is almost always 99.9% of the time is right there. Okay. To figure out which one is which, you have to do a depends on sentence. And then you put your units in those blanks, and you can figure out which one should be x and which one should be y. This would be your dependent because it depends on the independent. Okay. And so you'd fill in the blank with your units and what you're graphing, and make sure you have your x and y in the correct spot. Okay. And any questions? Okay, so kind of a lot of information review that we reviewed so far this unit, as well as a bit from last year, and some new stuff as well. So let's look at some situations and come up with some graphs. Which graph best represents the following rates of change? The temperature of a cup of hot tea over time. So what's going to happen? What's going to happen with the temperature? Is the temperature going to start low or high? High. Okay, and then what's going to happen over time? The temperature is going to drop and decrease. Eventually it's going to level out. Why will it level out? What's it reaching?
Room temperature.
Exactly, it's reaching room temperature. So we won't do any calculations, but we think about the situation. What graph represents a line like that? Graph B. Okay, so this would be temperature, and it will be in degrees Celsius. You put your units in brackets. And the other axis, your independent variable, that would be time. And time's probably in hours or minutes. Okay, you can put that unit in brackets. Next one, the speed of a bike over time as a rider bikes up and down a steep hill. So when you're at the bottom of the hill, what's happening? When you go up a hill, do you like stop your bike, or what do you do?
Go fast.
Go fast, right? But then as the hill, you start going up the hill, what's going to happen to your speed? It's going to decrease because you're going uphill. And eventually you reach the top and it kind of plateaus, and then you start going down the hill, and what happens? Your speed increases. Hold up. No. It goes up the hill first. So if this is your speed, right, your speed will decrease. Hold up. Your speed will decrease, and then your speed will increase. Thank you. Okay. Good. So that's going to be graph D. So this will be time, and this will be speed. Okay. Next one, a car accelerating at a constant speed. Underline the word constant. What does the word constant mean? Straight line. Okay, it's the slope's not changing. So this would be time, and this would be accelerating. Okay. So let's see here. This is graph B. This is graph D. This is graph A. The last one, a football kicked across a field. Height goes up and then comes back down. So this is graph C. Okay, the football does not start way high in the air. It starts at the kicker's foot, goes up, and then goes back down. Listed independent dependent variables on the graphs. We did that. So we labeled acceleration and time, height and time, temperature time, speed and time. Okay. Good. So summary. Straight lines, constant rate of change. Okay. The steepness indicates the rate at which one quantity is changing in relation to another. Okay, so curves are used when the rate of change is not constant. Now, a horizontal line means no rate of change. So right here, if we graphed simply a straight line, there is no rate of change. Something's still happening, but there's no change in temperature or speed or acceleration or height. Okay? Good. B. Here's a little graph of an airplane, okay, as a function of time. So how long was the plane in the air? Oh, you look at the graph, the last point is plotted 15 minutes, so you'd say 15 minutes. What was the plane's maximum height? Oh, got up to this high, that should be 6 is wrong, half marks. Meters. Okay, now you can just use M if you want. 6 meters. So you should, right here underneath height, put down M. This person forgot to put down their units, and that's wrong. Units always go in brackets. Okay. What's the total, underline total, vertical distance? So vertical is up and down distance. So from A to B, what's the total vertical distance? 6 meters. B to C, any change? No. What about C to D? 2. What about D to E? 2. What about E to F? So what's the total change in all the distance that was traveled by the plane, up and down? 6 plus 2 plus 2 plus 6. 16 meters. Okay. So a total of 16 meters up and down. Okay. So now we have to describe the plane's journey for each segment of the graph. What happened from A to B? What did the plane do? Right. So planes don't, when they take off, when they leave the ground, we say they take off. So plane took off. And did what? ascended, right? Ascended, increased the height, rose, something like that. You got a whole bunch of English words you can use, not French, English words. So who wants to choose one? Haley. Good. So increased the height by 6 meters over how long? What happened on the other axis? Over 3 minutes. Okay. At, now what else can we say about that line? Is it curved? No, it's straight. So what do straight lines mean? At a constant rate of change. Okay. So it didn't instantaneously jump up. It didn't slowly rise and then increase faster. It just went at a nice steady increase up to 6 meters. Okay. B to C, what happened? There it is. It's flat, so no rate of change. And that's because there's no change in height for 2 minutes. Okay? So there's no rate of change, no change in height for 2 minutes. What about C to D? What happened? Well, something got somehow described that the plane went down. So decrease of 2 meters in height over how long? 4 minutes at a constant rate of change. Okay. Then what? D to E. What happened there? Not a decrease, but increase in height of 2 meters over how many minutes? 4 minutes at a constant rate of change. Okay. And our last segment, E to F. What happened at this segment? The plane not ascended, but descended and landed so there's a decrease of 6 meters over 2 minutes at a constant rate of change. Okay. Now, you can write these as slightly different. Everyone should have slightly different sentences. That's normal. What's not normal is that everyone has the exact same answer in the back of the book. Okay? So that's not normal. For example, EF, I can say there is a constant decrease of 6 meters over 2 minutes. Now I know that constant means is a constant rate of change. Okay? But you have to make sure that you understand that as well, what you're writing. So you can write things a little bit differently. But you want to talk about the slope. That wasn't instantaneous decreases, but it's a constant decrease of how long over how long. Okay? And plane taking off and landing, that's kind of important stuff that you should tell as well. So we know we're back down at 0. Okay. Any questions? Okay, turn the page over, have a read of the next side. I want you to tell me what's the domain and the range. What's your dependent and your independent? What's your x, what's your y? For both sets of data, both graphs. Okay, so what we're looking at, you can get that later. Okay. Do depends on. You want to make sure that they have their chart in the right format. So this is the dependent and this is the independent. So let's put in here. Time depends on the number of bees. Is that correct? No. So they should be switched. Okay. So we take time, we put it over here. We take bees, put it over there. Okay. There you go. The number of bees depends on time. Is that correct? Well, it sounds a lot better. It is correct. So time is your independent. It is your domain. It is your x values. The number of bees then would be your y values. Your independent. Sorry, I said that backwards. It's your dependent. So y is your dependent. And it is your range. Okay. Good. So let's graph that one, see what that looks like. So graph the data for both. Should you join the points, do the graphs represent a function? We'll answer that as we graph. First thing I want you to do is put down your axes. Okay. So you should draw your axes right here. Okay. Now, let's put down our what we're graphing where. So this will be time, and it's in hours, so hours should be in brackets. This here is the number of bees, and there's no units for number of bees. Number of bees is just number of bees. So there's no units for that. So let's count the squares that we have. Each going up, we have 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 squares. So for the number of bees, we have 18 squares. The number of bees range from 1 to 26. So how many bees can we represent for each square? We go 26 divided by 18. And it's 1.44. So if each square is 1.44, that would take up our entire graph, which we want. What we're trying to avoid is just graphing all our data in this little bit of grid. We want to use the whole grid to make a whole big picture. Okay? So if we use 1.44, we would use up our entire range, which is good. But 1.44 is kind of weird. So we could go up by 1.5, but that's still a little hard to graph. What's an easier number to graph? If we go up by 2. So 2 bees per square. So we can start at 0. I should erase all these ticks. And you should definitely graph in pencil. And go up by 2. 2, 4, 6, 8, 10. And I'm going to label 10. I'm not going to write all the numbers. You don't need to. That's too much information. It ruins the picture. 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Okay? So we should still get a pretty good picture for the number of bees. All right. Then we have for that time starts from 5 to 19. So our domain, 9 minus 5, means we did this over how many hours? We have 14 hours. So how many squares do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So for time, we have 19 squares. So 14 divided by 19 equals how much? We don't even really need to do this. 0.736. So we should say that we have 1 hour per square. Okay? So if we have 1 hour per square, we should have enough. Now we want to start at 5. Because that's when we started measuring. So what we do is we do one of these squiggly lines. That means we're taking a piece of the graph. Right? Here's our graph. We don't start measuring until this point. So we're cutting this out and removing it. So all we do is take this, move it away, so that we don't have this useless piece of graph there. And so all we have now is where we started plotting our data from, 5. And you got to be careful when you do this. Okay, but for me, we start at 5. So let's start at 5. 6, 7, 8, 9, 10. 15. 20. Okay, that's our last tick. And when you're writing the numbers, you should make that tick a little longer. Right? So there's a difference between short ticks and long ticks. That way it helps you plot your graph accurately. So we've taken a piece of the graph away because it's not needed. That way we can use our graph paper much better. Before we start plotting our points, we're missing one other thing on our graph. What goes on the top? Title. So number of bees throughout the day. Okay. All right. So time 5, we had 2 bees. And now you can plot your data. Okay, go ahead and plot your data, please. You don't always have to be in the corner of a grid, right? The second point, time is 7 on a line, but your number of bees is 5. Okay, so this 5 is going to be in between 4 and 6. (13) 21. 21 will not be on this line, but 13 will be. Okay, there's 19 and 1. Do you see a straight line anywhere? Any kind of relationship at all? No. Okay. So should we join the points? Well, we shouldn't join the points, not for that graph. Is it a function? Yep, it's a function. Right? There's each input has one output. So it's a function. Okay, so let's do the next one. First thing is, draw your axes. Go. Okay, label your axes. So you have to do a depends on sentence. What should be the depends on? Does time depend on temperature, or temperature depend on time? Well, it makes more sense for temperature of the hive to depend on the time of day. Okay. So this is your X, it's your independent. And this is Y, it's your dependent. Okay. So this would be X. So time again is in hours. That should go in brackets. And temperature, it's degrees Celsius. It should go in brackets. Okay. All right. Title, what would be a good title? What are you graphing? Temperature of the hive throughout the day. So your time goes from 5 to 19 again, and it's exactly the same. So time, we can do the squiggly line on the bottom, start at 5 and go up just like we did the last graph. So we're up by ones, 1 hour each time. What about temperature now? Your low temperature is 12 and your high temperature is 26. So 26 minus 21, what is that? Sorry, 26 minus 12. Is that 9? So there's a range of 9. And how many squares do we have again? Going up, we have 18. So that'll be 0.5 degrees Celsius per square. Do you think that'd be easy to plot? No. So which would you go up to? What would be better? Be 1 degree Celsius per square. Okay. Question? Did I have this wrong? What? Oh. Okay, so do your squiggly line again. Squiggle, squiggle, squiggle. And you can start at temperature of 12. 13, 14, there's 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Okay, go ahead, plot your points. You have. How could you get that wrong? I can't believe it. Okay. Yeah, 14. So what is that then? 14 divided by 18? Still less than 1, right? Yeah, 0.7. Okay. So we won't have to change our grid lines. Okay. We can still go up by 1 degree Celsius and we'll be fine. But make sure you use the squiggly line to show that we took off a section of the graph. Okay? So from 0, we do jump up. Okay. Plot your points. Don't wait for me to do it. With a 2, that's 20. Okay. Should we connect the points here? Do you guys see a relationship here? What's happened to the temperature? Kind of, right? So what we can do, and it kind of makes sense because what are we graphing over here on the left? Number of bees. Does it make sense to have a value between, say, 20 and 21? What would that look like? 20.75 of a bee? What's 0.75 of a bee? Never seen one of those flying around.
Missing a wing.
Yeah, missing a wing. The only time you see that is when you step on it, but you won't find that in the beehive. Okay? So this is a number of bees. It doesn't make sense to have values in between because they're whole numbers. Okay? But what about temperature? Does it make sense that in between 15 and 16 degrees there was a slight increase of temperature? Totally. It wasn't instantaneous. It didn't go jump right from 15 up to 19. It didn't go boom, they were at 19. What happened? It slowly increased. So for the temperature, it makes sense to have points in between. So for this graph, it makes sense to connect the dots. And we try and connect the dots with a straight line or with a smooth curve. Okay? So this would be a smooth curve. On my desk. Okay. So we have two different types of graph. We have two different types of data. We have discrete data on the left. Okay. On the left is discrete data. Data values on a graph that are whole numbers. You can't go to Superstore. Nice job. Can't go to Superstore, and if you can find it, buy half a jug of milk. Right? Because if you go in there and cut a milk jug in half, probably going to have your head bouncing off the front of a police car. Not going to go well for you. Okay, so whole numbers, you can't split up. Yeah, if you want to try and prove it wrong, go ahead. Just let me know so I have my camera ready. Okay, can't split up. Okay, whereas data values, continuous data, that's the graph on the right. Okay, data values and graph that are easy to split up. They're going to have decimals. Such things as temperature, height. Right? They are not whole numbers. Those are only examples of continuous data. And for when you graph discrete data, you only show the points. That's because the values in between have no meaning. Now you see this done wrong in the newspaper all the time. they'll connect dots when they shouldn't. There's an exception. Exception, yes. The exception is when you graph large discrete values. Okay. If you're graphing large discrete values, then you would connect them. So if I'm graphing the number of houses sold, right? If I'm at 0, this is 5, and that's 10, I would graph these as discrete values that are not connected. But if I'm graphing the exact same thing, except now I'm graphing the number of houses sold in Canada, if I'm graphing 0, 1,000, and 2,000, I would then still be graphing discrete data, but I would actually go and connect these dots. And that's because between 1,000 and 2,000, there's numbers in between there. 1,001, 1,002, 1,003. So that way it actually makes sense to connect the dots. Whereas in between 5 and 10, there's very few values in there, so I would not connect the dots in that graph. Okay? So you got to be careful with continuous and discrete data. Any questions? What time is it? Quiz time! Woohoo! All right.